In this section, we're going to be covering pedigrees. As you can see, this is what a sample pedigree looks like. And essentially, we can use these diagrams to predict different inheritance patterns of certain traits, as well as we can also look at how certain diseases or traits can possibly show up in future generations. So just to get a basic understanding of how pedigrees work, if an individual is shaded, it means that they are affected or showing the trait that we're investigating. So let's say I'm looking at individuals that have hemophilia, which is a condition. The ones that are shaded will definitely be affected, whereas the ones that are not shaded, they're not affected. If you see a square, that means that is a male, and a circle denotes a female. A line that you see here suggests that they've had children, and the offspring are displayed through the lines below. Another thing that pedigrees will include on the side are these generation numbers. These generations can be used if I'm trying to refer to some individuals. So if I wrote in Roman numerals the number 3 and then a 2, that means I'm referring to this individual here in the third generation and then the second one. And here are also some other symbols. So again, shaded meaning affected, unshaded meaning unaffected. If the sex is unspecified, then they can show this diamond notation. We already looked at this marriage line, and double lines means marriage of blood relatives. With twins, you might see a line appearing in this V format. And another notable thing is you might see some squares or circles being half shaded. If they are half shaded, it means that they are carriers of a certain condition. So they're not affected themselves, so you're mainly going to find that with recessive conditions. So now that you have an understanding of what pedigrees look like, we're going to use that knowledge to predict what kind of inheritance pattern some conditions are. So whether it's autosomal dominant or recessive, or sex-linked dominant or recessive. We can then also use this to make predictions of future generations and offspring. So let's have a look at the first case. So if a trait is autosomal recessive. So if I say that a trait is autosomal recessive, let's say I'm using the letter little r, that means that this little r is going to denote for a certain disease or suggest that the individual is affected. Now remember, an individual's genotype is composed of 2 alleles, one that you inherit from each parent. So in this case, if someone had little r, they would be affected. If someone had capital R, little r, or capital R, then these two genotypes would be unaffected. Now I'm going to run you through some general characteristics of autosomal recessive traits, and at the end I'm going to actually highlight what are the most important ones that we should look out for when you're first looking at a pedigree. So here are some general characteristics. If you find 2 parents that are affected, then all offspring will also be affected. So if you think about it, if the 2 parents are affected, then they're going to have the little r genotypes. And if I do a Punnett square with this, then all the offspring would also present the same genotype. So 100% of the offspring will be affected. Another thing that you might find is that unaffected parents may have affected children. So as you can see here to the right, you can see 2 parents that are unaffected, yet they have an affected offspring. This is one of the main things that you can look out for. Now, the reason for that is these parents may actually be heterozygous. So remember that an individual is going to inherit 1 allele from each parent. So without me even doing a Punnett square, I can tell that this affected individual would have inherited the little r allele from each parent. Now, this could only be possible if the parents are heterozygous and carriers of the recessive allele. So the parents are not affected themselves, but they are carrying that recessive allele, which makes an individual affected. Hence, this is a total giveaway sign that this is going to be a recessive trait. If I were to look at a pedigree, the first thing I would try to look out for is this scenario here. If 2 unaffected parents have an affected child, I can automatically tell it's a recessive condition. But you do need to then go and assess whether it's going to be sex-linked or not. These are steps I'm going to follow through with you guys right at the end. Another characteristic of autosomal recessive conditions is that the trait is likely to skip generations. So as you can even tell in this example here, if some individuals are heterozygous, they're not being affected themselves, but they can pass on the recessive alleles to their children, making them affected. So you might find some generations have completely unaffected individuals, but in the next generation, the condition may appear. So that is because some individuals are heterozygous for the trait and not affected themselves. Now going to autosomal dominant conditions. So autosomal dominant means that the capital R is now going to be the affected allele. So now it's going to be the complete opposite. These two first genotypes is going to be for affected individuals, whereas if you're homozygous recessive, that means you're going to be unaffected. Now, as you can just see, even by these genotypes, this trait is more likely to show up in every generation. And now another key characteristic is that two affected parents may have an unaffected offspring, as you can see in this example here. Now, once again, this is a giveaway sign that it is a dominant condition. So how come this can be the case? Once again, the parents may have this heterozygous genotype, so they could be both affected, and somehow they may pass the unaffected little r allele to the offspring. So if parents are heterozygous for the trait, they can pass on the normal recessive allele to children. The next option we have is a sex-linked recessive condition. So once again, it's the little r that's going to be affected, but with sex-linked conditions, we always put the X chromosome right underneath that little letter. So this allele is affected. Now remember, with sex-linked conditions, it's linked to an individual's gender. So you're going to find that this characteristic is going to be more common in males. As you can even see in this pedigree, you have 5 males here being affected and 3 females being affected. So definitely males are overpowering in this scenario. Now, why is that the case? It's because males only have one X chromosome. So if they, by any chance, inherit the little r recessive allele, they're automatically going to be affected. Now, this is going back to the idea that the Y chromosome is a lot shorter than the X chromosome, so it's missing a lot of genes, and hence all the traits are only going to be presented on the X chromosome. If you'd like more detail on this, you can go back to the inheritance patterns module to have a better understanding of sex-linked conditions. Next, if a female is affected, then all sons will show this trait. Now let's use a Punnett square to actually verify this statement. So if a female is affected, she's going to have this genotype. And if a male is affected, then the male is going to have this genotype. Now, in this scenario, it doesn't really matter what the father's genotype is going to be. So I'll leave that as blank. I'll put a question mark on top of the X for the male. Now, if I were to only look at the male offspring, then this is going to be their genotype. So as you can see here, all of the male offspring will be affected. Now, if you have a male offspring, they will always inherit the Y chromosome from the father. So that leaves them being able to inherit the X chromosome just from the mother. Now, if you imagine, if both of the mother's X chromosomes are carrying an affected recessive allele, that means that there is a 100% chance that that offspring is also going to carry that little r allele. So here's a summary of what we just worked on. And lastly, you've got sex-linked dominant conditions. So for sex-linked dominant conditions, it means an X with a capital R on top is the affected allele. Now, the main thing that will give it away if it's sex-linked dominant is that if a male is affected, then all daughters will show this trait, but not sons. So an affected male is going to have this genotype over here, and an affected daughter just needs to have one copy of that dominant allele. So they could either be homozygous or they could be heterozygous. But either way, they just need one copy of that R allele. Now, if I did a Punnett square again, let's go and write the male father's genotype. The mother's genotype, I'm not concerned with, so she could be anything. And if I draw this out and only look at the female offspring, you will see that they always inherit one X chromosome from the father. And if that one X chromosome from the father is carrying that dominant recessive allele, then they will also carry that same allele. So I've left the question marks there because we don't know the mother's genotype, but either way, no matter what it is, all the daughters will be affected. And if I look at the pedigree, I can actually see this pattern. So this is an affected male, and all is the offspring, which are daughters, are also presenting the trait. And I also want to go back to the sex-linked recessive condition. So from this one, we concluded that if a female is affected, then all sons will show this trait. Now we can see the same thing in the pedigree here. So if I have an affected female, then all her sons are also showing this trait. So you've learned all of the general characteristics, but how do we actually apply it step by step to a pedigree question? So I've summarized all of the key points in this table above, so you can use this for your questions. But this 3-step approach here will make it so much easier for you to answer any pedigree question. So the first step here is determine if the trait is recessive or dominant. Now you're going to try and look out for either 2 affected parents that have an unaffected offspring. And if you see anything like this, you can automatically assume that it's going to be dominant. And if you see that you have 2 unaffected parents with an affected offspring, then you'll automatically assume that it is a recessive condition. And I've already explained to you in terms of the genotypes why that will be the case. So remember, with recessive conditions, if you have 2 unaffected parents, they could be heterozygous and they could be carriers of that recessive affected allele, which can then pass on to the offspring. Same thing with dominant. If you have 2 affected parents, they could be heterozygous and they could be carrying that little r normal allele, unaffected allele, which is passed on to offspring. So these scenarios are absolutely unique to either being a recessive or a dominant condition. Next, we need to determine if it's sex-linked. So in that pedigree, once you've already ruled out whether it's recessive or dominant, look out for either one of the following. So if you see an affected father has all daughters affected, it's going to be sex-linked dominant. And if you see an affected mother has all sons affected, then it's going to be sex-linked recessive. And lastly, I would definitely still be using Punnett squares to verify these statements. Especially if none of these above rules even apply, then you're going to be relying on Punnett squares and some of the other hints that we've looked at to give you an idea of what kind of inheritance pattern it may be. And here's a little summary of what we've just discussed. So now we're going to be looking at some practice questions. So a lot of them are coming from HSC papers directly. So you can definitely have a look at the style of questions that could be asked. So in this case, you can see an inherited characteristic in a family is mapped out in the pedigree shown. The inheritance of the characteristic is either autosomal recessive, sex-linked recessive, autosomal dominant, or sex-linked dominant. So we're going to be using that 3 steps that I've given you that will help you identify and answer any kind of pedigree question. So first thing, determine if the trait is recessive or dominant. So I'm going to be looking out for either one of these scenarios. 2 unaffected parents with an affected child, or the other case, 2 affected parents with an unaffected offspring. In this question, it's great. My life has been made super easy because we can spot we have 2 unaffected parents with an affected child. So this is automatically going to tell me that the condition is going to be recessive. And what I can now rule out is options C and D. So we've already done step 1 here. It's a recessive condition. Step 2 will be to check if it's sex-linked. So to determine if it's sex-linked recessive, we'll have to see a pattern like this. So an affected mother would have all sons being affected. So let's look out for this scenario. So in this pedigree, I can't actually spot an affected mother. All of these mothers are unaffected. So I'm not able to quickly apply that rule. So what I'm going to have to resort to is doing Punnett squares, or actually specifically looking at the genotypes of this individual. The best way to approach this is assume that the condition is already sex-linked recessive. And we're going to try and look for any contradictions. This father here is affected, so this is going to be their genotype. And the offspring here, this female, is also affected. So we definitely know these 2 genotypes. Now the mother there is unaffected, so hypothetically, she could be either one of these genotypes. So she could either be homozygous dominant, or she could be heterozygous. Now, if you're ever in a situation where you don't know which one it could be, the only way that you can work this out is either by looking at that individual's parents or looking at the offspring. So if we already know that this child is affected, let's see where she's inheriting each allele from. So this child is definitely going to inherit one of the little r alleles from the father. So that leaves her with the other X allele, and that also has to come from the mother. So hence this mother can only be heterozygous for the trait. So now I definitely know her genotype. Let's have a look at the other daughter. So this daughter is unaffected, meaning that she definitely carries that dominant allele. Now the only way that she can inherit this allele, the father definitely doesn't have it. So she must have inherited that from the mother. So that leaves her with the other X chromosome, which comes from the father. So she would have inherited this specific allele from the father. So that daughter is heterozygous. So up until now, this all makes sense. There's no contradictions, but I'm still going to keep going to see if there's anything that could contradict my point over here. So here, let's look at the one that I've boxed with the red dotted lines. That father there is unaffected, so definitely carrying that dominant allele. Now on the left here, we've got an affected female. An affected female can only have this genotype. Now, is it possible for this child to get this specific genotype if the condition is sex-linked? Let's have a look. Now, as I mentioned earlier, a female daughter is always going to inherit one X chromosome from the father, which leaves her only with this option. So her genotype is definitely going to start with X capital R. Now, this is absolutely contradicting what she should be, which is homozygous recessive. No matter what she's inheriting from the mother, if I assume that the condition was sex-linked recessive, then this daughter should actually show up as unaffected. So this is a big contradiction. We definitely cannot assume that this condition is sex-linked recessive. So I would rule that one out. So now my answer would be A. So question number 2, a pedigree is shown. What type of inheritance is shown in the pedigree? So again, step 1, determine if it's recessive or a dominant condition. We're going to be looking out for either one of these scenarios here once again. So I would recommend screenshotting this and having this on the side as we do all of these questions. Now I can spot it exactly here. I have 2 affected parents that have an unaffected offspring. This would only be possible with a dominant condition. So remember that capital R allele is going to be affected, meaning that these parents are going to be heterozygous and affected, and they would have an offspring that inherits the little r allele from both of the parents. Step 2, determine if it's sex-linked. So let's see if we can actually spot this rule this time. So if an affected father has all daughters that are also affected, then it's sex-linked dominant. Now I do see an affected father over here, and hypothetically if it was sex-linked, I would have to see that his daughters are also affected. Now, as you can see, there's a contradiction here. So we can definitely rule out that it's going to be a sex-linked dominant condition. Hence, my answer would be D, non-sex-linked dominant. All right, let's have a look at this next pedigree here. So again, we're looking out for 2 either affected parents or unaffected parents. And in this scenario, we can see here we have 2 affected parents that have unaffected offspring. So this will tell me it's a dominant condition. Now, step 2, look out for whether it's sex-linked. So remember, with sex-linked dominant conditions, we're looking for an affected father and seeing if all of his daughters are also affected. So here we see an affected father and his daughters. There's some daughters here that are unaffected. So this completely contradicts the idea that this could be sex-linked. So my answer would be C, non-sex-linked and dominant. All right, so in this next question, which human pedigree shows the inheritance of a recessive sex-linked characteristic? For this question, we're going to assume whenever we're looking at the genotypes that each of these pedigrees are showing us a sex-linked recessive condition. And the idea is that we're going to look for contradictions here as well. All right, so option number A. Here we've got a father that is unaffected. So capital R and Y. Now, a big giveaway sign is that daughters will always inherit the father's X chromosome. So no matter what, this daughter would definitely need to have the X with the capital R coming from the father in her genotype. Now, regardless of whatever she inherits from the mother, so no matter what kind of X chromosome she gets from the mother, this capital R is definitely going to dominate. So remember, if it's a sex-linked recessive condition, a capital R would mean that the individual would be unaffected. So this is contradicting because in the pedigree here, we're seeing a daughter that is shaded. So option A would definitely be ruled out. It doesn't make sense for this to be a sex-linked recessive condition. On to B. Again, I just like to start off with looking at the father and seeing how that impacts his daughters. So if this father is unaffected, once again, they're going to have the same genotype here. And we're seeing the same pattern. We're seeing a daughter that is affected when this is following that exact same pattern from option A. This daughter will definitely be inheriting this X chromosome from the father. So her genotype will definitely have the X with the capital R allele. And no matter whatever she inherits from the mother, this should be unshaded. So again, B does not make sense either. It can't be sex-linked recessive. Okay, now C, the father here is affected. So a little r at the top with the Y, meaning that this daughter here will definitely have this allele. We can start with that. Now the mother is also affected, so we can actually be sure of her genotype. She's going to be homozygous recessive. So the second X chromosome that the daughter inherits coming from the mother, no matter what, will definitely carry that little r allele. So this means that in this scenario, this daughter should be affected if she has this genotype. So the pedigree should actually show this as being shaded. So C also isn't an option. And lastly, let's have a look at D. So this one should work perfectly since it's our last option. So the female here is unaffected, the male is affected. So if male is going to have the little r and the Y. The female is unaffected, she definitely has a capital R as its allele. I'm not sure yet what the second allele is going to look like, so I'll leave it as blank for now. The daughter is affected, so she's going to have XX, little r, little r. Now we already know that this X chromosome from the father, that daughter will definitely be inheriting that. So that only leaves us with the possibility that the other X chromosome is coming from mother. So now we've been able to determine what the mother's genotype is going to be like. So for the son's genotype, he's definitely inheriting the Y chromosome from the father, leaving him inheriting the X chromosome from the mother. So the mother now has both options. She has the recessive allele and the dominant allele. So since that male is unaffected, he will definitely be taking the dominant R allele. And this absolutely makes sense, so D will be my answer. All right, next question. The pedigree shows the inheritance of a genetic disorder. Which row of the table correctly identifies the two possible types of inheritance for this disorder? So our life is going to be so much easier with 3 steps we've learned. So in the red box here, I'm seeing 2 affected parents with an unaffected daughter. That tells me it's a dominant condition. So it's definitely not going to be recessive. So I can rule out all of the options that contain recessive as an answer. And that was pretty easy now. I'm only left with option A. So that's going to be my answer. So see how those steps made it so easy to answer this. I didn't have to look at any genotypes. And with this multiple choice question, I was immediately able to rule out all the options that won't work. Now we're going to be looking at more worded pedigree questions. So for these ones, it's really important that number 1, you get the inheritance pattern correct, which we've practiced with the multiple choice questions. But number 2, when you're asked to explain how you came to that reasoning, you need to be really particular with how you go about answering it. So you don't just want to state the rules that we've learned. You actually want to explain, maybe through genotypes or through Punnett squares, how you're reaching that conclusion. So for this question, a pedigree chart of an inherited characteristic is shown. Subsequent genetic analysis shows that individual in generation 1, number 2, does not have the recessive allele. Explain the inheritance of this characteristic. Starting with step 1, let's work out if it's dominant or recessive. In this scenario, I'm seeing 2 unaffected parents with an affected offspring. So that will immediately tell me that it's going to be a recessive condition. Secondly, let's see if it could be sex-linked. So with sex-linked recessive conditions, an affected mother will have all sons being affected. As you can see here, we've got an affected mother and all of the sons are affected. So this is a strong indication that this could be a sex-linked recessive condition. Now this question's also given us a hint that this individual in generation 1, number 2, does not have the recessive allele. So from our initial analysis, I'm already fairly certain that it would be sex-linked recessive, but just to make sure, I'll show you what the genotypes would look like if we assumed that the condition is autosomal recessive. If we start off with this individual here who is unaffected, he only has 2 possible genotypes. But the question's already told us that this person does not have the recessive allele at all. So going by that scenario, this individual would be homozygous dominant for the condition. Whereas individual number 1 is affected, so they would be homozygous recessive. As you can see in the Punnett square here, if that was the case, then 100% of the offspring would be unaffected. Now this isn't reflecting the So the condition has to be sex-linked recessive. Now let's map out the genotypes just to be 100% sure. This male is unaffected, so that would be the genotype there. This is an affected female, so she would have 2 of the little r alleles. So from that Punnett square here, if I cross the 2 parents, I see a female here that's unaffected, another female that's unaffected. So all females should be unaffected. And I have 2 males that have the little r allele, so the males should be affected. And this is as we can see in this pedigree here as well. So nothing is contradicting the Punnett square there. I've just written out all of the genotypes of the offspring. Now looking at the couple in generation 2, the male here is unaffected, so they would have capital R in their genotype. Now I've also done a Punnett square on the left there. So if I look at all of the offspring, this male who is affected has this genotype, and we can see that is a possibility from the Punnett square. We have 2 unaffected females, so they could have either one of these genotypes, doesn't matter. So there's no obvious contradictions there. And then we also have a male here who is unaffected. So we also see that this genotype is a possibility for the male. So everything's working well, there's no contradictions. I can definitely then say that it's a sex-linked recessive condition. Okay, so this is actually a 3 marker. So with your explanation, you do need to be really particular with what points that you're giving to convince the marker that this definitely would be a sex-linked recessive condition. So you don't need to mention everything that we've just looked at. We're going to be really specific with our points here. So the first step to answering this question, I would start with telling the marker that this condition has to be recessive, since we have 2 unaffected parents here with an affected offspring. Now, simply just stating it like this isn't going to get you the marks. You actually need to be specific with what individuals you're mentioning, and you also need to specifically mention or talk about their genotypes. So be specific. As you can see in my answer here, I start off with mentioning that these individuals, individual 1 and 2 in generation 2, so these 2, are unaffected, but they have a child in generation 3, number 1, who is affected. So that is the rule that we learnt, and I'm applying it to this question and showing the marker that I'm directly engaging with the stimulus by actually writing down which specific individuals I'm talking about. I then go and say that this suggests that the condition must be recessive, and here is the key bit. So I've gone to actually explain the statement here. So this suggests that at least one parent must be carrying the recessive allele. It's going back to this diagram here. So if it's an autosomal condition, then these parents will be carrying the recessive allele, passing it on to their offspring. Now, the same sort of concept also applies to sex-linked conditions. So again, the parents, they're masked by the dominant R allele, but we can see that the female here is carrying that little r. So this can somehow appear in the offspring, and specifically we're seeing it with the male. That is then left with the recessive allele and is found to be expressing it and is affected. Next, we'll look at the rule that we apply for sex-linked recessive conditions. So for them, we always see an affected mother has all sons affected. Now, specifically, I'm going to state the genotypes of these individuals. So the mother has this genotype, and so she will definitely be giving one of her X chromosomes to all of her sons, leaving them also affected. Here I've written out the same thing, except I've supported it with my Punnett squares. So I say that more specifically, the condition must be sex-linked recessive, as individuals in generation 1, number 2, would have this genotype, and individual 1 in generation 1 must have this genotype. And here's how I'd write it out. So I would say that more specifically, the condition must be sex-linked recessive, as the individual in generation 1, number 2, would have this genotype, and the mother would have the following genotype here. Then I also show the Punnett squares. So the Punnett squares are really important. They help to support your answer, and it is a good thing to include when you're looking at these pedigree questions. So always beneficial, and the markers will definitely be looking at your Punnett squares if you add them in. As expected, all sons, and I've also specified the sons, they are affected as they inherit the XR allele from their affected mother. So this is super important. I'm not just stating the rule that we learned, I'm actually explaining it. So without this explanation, my answer would be a lot weaker. Now this explanation would be sufficient, but if you wanted to add anything else, you could also then argue that the condition can't be autosomal recessive, because as we looked at in the previous case here, it would mean that all of the offspring should be unaffected, which isn't true. So if I wanted to talk about that, I could explain it in this sense. So the condition can't be autosomal recessive, as individual here would have to have the homozygous dominant genotype, and the mother would be homozygous recessive, resulting in all offspring being unaffected. And this contradicts the generation 2 offsprings in the pedigree. On to our level 3 questions. So one of the genes involved in determining the color of a species of fish has 2 alleles, yellow and orange. The diagram shows a pedigree chart for the inheritance of color in the fish. Use the pedigree chart to explain why the yellow allele is recessive. So the yellow individuals are the ones that have been shaded. As you can see that you have parents that don't have the yellow allele, and somehow we have offspring that are exhibiting and expressing the yellow allele. So that's going to be the basis of my answer. Now, just to remind you guys, in terms of the genotypes, I'm just going to write a little legend here. Little r meaning yellow, capital R meaning orange. So I'm seeing that offspring have little r's, the affected ones that have the yellow. The only possibility for this would be if the parents are heterozygous. So the dominant orange allele, which is the capital R, is being expressed, but the recessive allele that gives you the yellow phenotype is going to be passed on to these offspring that are expressing it. So for 2 marks, my explanation would be that the inheritance of yellow color is recessive, since both parents are orange, but they have offspring that are yellow. The yellow allele must be present in both parents, but it is not being expressed, and instead it would be passed down to these offspring. So this is a way they can write it, or if you want, you can talk about the genotypes like we've done in the previous questions. Next, explain how a cross between individuals 1 and 2 could be used to determine whether the inheritance of color in the fish is sex-linked or autosomal. So we're essentially going to have to go through these 2 different scenarios and assume both cases and see what the results could be. All right, let's explore the 2 different options. First, let's look at sex-linked. So we're looking at these 2 individuals. If they are sex-linked, then this will be their genotypes. So you're going to have the affected female, which is going to be homozygous recessive, and therefore will display the yellow allele. And then you're also going to have the male who is unaffected, and hence he would have the capital R on its X chromosome, and therefore going to be orange. Now let's do a Punnett square. When you're doing this and you're introducing new letters that are not in the question, it's always good practice to include this on the side of your Punnett square to show the marker what each letters represent. So in this case, I did the Punnett square. I put the male and the female on the side, and here are my results. So I'm seeing that in the female category, 100% of the females would be orange, and 100% of the males would have the yellow phenotype. So this is my result. All males will be yellow and all females will be orange. Now, if it was autosomal, on the other hand, we'd be able to determine this person's genotype. They would just be little r. But this person could either be homozygous or could be heterozygous. Now remember, if you don't know what the exact genotype could be, the only way you can figure that out is by looking at that person's parents or their offspring. So to work out which one it could be, we have to look at the parents here. So the parents could also have either one of these options. We don't really have enough data to determine which one it could be. Now, since the parents could be either one of these options, individual 1 could also present either one of these genotypes. So for autosomal case, we may even have to divide this into 2 separate scenarios. Scenario number 1 could be if individual I had this genotype, and number 2 could be the following. Looking at scenario number 1, we've got the affected female, and we've got the male here, assuming that they are heterozygous. From this, so with autosomal, it doesn't matter with gender. In terms of all of the offspring, we would see a 50% chance of them being yellow and 50% being orange, regardless of what the gender is. Then scenario number 2, we look at this individual being homozygous. If that is the case, then 100% of the offspring would be orange. So in your answer, it is good if you break down both of these scenarios, and especially with autosomal, if you divide them into 2 different categories here. But to get the full marks, or to make sure that you are hitting that band 6 response, you would need one extra thing. So essentially, you would need to determine what point of difference could I be looking at in these offspring to immediately tell whether it's sex-linked or if it's autosomal. So here's the conclusion that I came up with. So if you go back to looking at the sex-linked conditions, we say that all males have to be yellow and all females have to be orange. If I find any contradictions to these results, I can then assume it's autosomal. So in my answer, I could say that the presence of an orange male, which would absolutely contradict a sex-linked condition, could lead us to assume that it is autosomal recessive. Or the other way you could present it is the absence of an orange male would tell me that it is sex-linked. So that was our plan in terms of how we write out the response. It's simply going to be including these Punnett squares and having some sort of a worded explanation to follow along. So first I go through the scenario of it being sex-linked. If the condition was sex-linked, I drew out the Punnett square and I explained what the genotype of individual 1 and 2 would be, as we've looked at here. And then I put these results in my answer. So all male offspring would be yellow and all female offspring would be orange. Insert Punnett square, and I've also included what these letters stand for. Second, we look at recessive. So if the condition was autosomal, then individual 1 could be homozygous or heterozygous, and individual 2 would be homozygous recessive. Result number 1. So if individual 1 is homozygous dominant, then 50% of the offspring would be yellow and 50% would be orange, as you can see in this Punnett square here. So this definitely helps to support your answer. So some questions may even have that a Punnett square has to be included in the marking criteria. So it's always good practice to include this in your answer. Result number 2, if individual 1 is heterozygous, then all male offspring would be orange. And finally, you have your conclusion or your point of difference in these results that would tell me which one it is. So therefore, the absence of an orange male would indicate that the condition is sex-linked. And our final question, analyze the pedigree below showing a genetic condition expressed in a family. Determine the pattern of inheritance shown in this pedigree and identify the genotypes of individuals 1 and 16. Use the letter capital A or little a to represent the alleles. We're seeing 2 unaffected parents with an affected offspring. That's telling me that it is a recessive condition. Now we have to test if it's sex-linked or not. If it's sex-linked, then an affected mother would have all sons being affected. We can see we have an affected mother here, and she also has sons. Ideally, all of the sons should be affected. This one is affected. However, this one is not showing up as affected. So this is a contradiction, so it cannot be sex-linked. So then I can say that the inheritance pattern for this case will be autosomal recessive. Genotype of individual 1 over here who's affected will be little a. And individual 16 who's unaffected. So this individual could be capital A, little a, or homozygous, so capital A, capital A. We can only really know by looking at the parents. So we can see individual 17 is affected, so definitely they would have little a, little a. For individual 17 to be affected and have little a as the genotype, the parents have to be heterozygous. So they would have to have these genotypes. Now, technically, looking at that, individual 16 could still be either one of these options. And you can see clearly here, I did the Punnett squares for individual 8 and 9. The results show that the offspring who are unaffected can be homozygous or heterozygous. So a bit of a trick question, this individual could be either one of these options. Part B, if individual 16 has a child with an affected partner who has the genetic condition, what are the chances that this child will be affected? Show any relevant working out. So again, we have two scenarios here. If individual 16 is either heterozygous or homozygous. Scenario number 1, if individual 16 is homozygous dominant. If I look at the Punnett square here, then all of the children here are unaffected. So in that scenario, there is a 0% chance of being affected. Then you have scenario number 2. So if individual 16 is capital A, little a, if I do the Punnett square here, you can see in this box, they're unaffected, unaffected, affected, and affected. So there is a 50% chance here of being affected. And now I don't just end here, since I don't know what the genotype of individual 16 is. My total probability will be out of all of these options. So I have 8 possibilities that I've investigated. And out of these 8, I see that 2 of them have the chance of being affected. So my total probability of it being affected will be 2 out of 8, which overall gives me a 25% chance of the children being affected.